Alright, so we want to graph this function. If you watched the last video, I had some steps for you to graph a function. Let's take a look at those. We want to determine the end behavior of a function by completing the leading coefficient test. So we want to know what the left side's doing, what the right side's doing. So remember, to do that, we have to look at the degree and look at the value of the leading coefficient. If it's an even degree, they're either both up or both down. If it's an odd degree, one side's up and one side's down, and use the leading coefficient to determine which. Calculate the zeros. That's when you set the entire function equal to 0. Then you factor and solve. You may have to use the quadratic formula. You want to list the x-intercepts, and the x-intercepts are just the real valued zeros. So really you did all the work for that in this step. And then use the multiplicity. Multiplicity is how many times the 0 shows up. If it has an odd multiplicity, the graph crosses over the x-axis at that 0. If it has even multiplicity, the graph just touches the x-axis and goes back the other way. Calculate the y-intercept. That's when you let x equal to 0 in your function. And then you can determine symmetry if you choose to. It's not required because sometimes a function doesn't have any symmetry. You can plot extra points, and this is terribly important, by picking points between and beyond every x-intercept. So we will follow all of these steps, except maybe not symmetry, to do this problem. So the very first step, we want to discuss end behavior. So what is the left side doing? What is the right side doing? And how do we determine that? Well, it's based on the degree of the polynomial and the leading coefficient. So let's take a look at the degree of this polynomial. And this polynomial is not expanded. So the degree we actually have to calculate. So notice there's an x squared right here if you were to multiply that out. And then there's an x to the first here. And when you multiply bases, you add exponents. So this would be an x to the third, which is a degree 3. And the leading coefficient is going to be negative 2 times 1 squared times 1, which is negative 2. And an odd degree and a negative leading coefficient leads us that the left side is pointing upward and the right side is pointing downward. So you need to have that leading coefficient test memorized to do end behavior. Next thing, you want to calculate zeros. So you have 0 equals negative 2 times x minus 2 squared times x minus 1. You could write that out further as saying negative 2 times x minus 2 times x minus 2 times x minus 1. Remember, a constant in the front does not give us a 0. So we will not get a 0 out of that constant. To prove that, you can just divide both sides by negative 2, and it simply disappears. And you don't have to show me that step. You can just ignore the negative 2 in the front. Now you see what I'm doing. I'm setting every factor equal to 0. Actually, the first one I went ahead and solved, but I really didn't want to do that. So let's go back and set x minus 2 equal to 0, x minus 2 equal to 0, and x minus 1 equal to 0. And this gives me x equals 2, another x equals 2, and x equals 1. Notice x equals 2 has a multiplicity of 2 because it showed up twice. And again, the multiplicity is how many times that 0 shows up. On the other hand, x equals 1 has a multiplicity of 1. It only showed up one time. Okay, now I would like to calculate the y-intercept. And so that's going to give me y equals negative 2 times 0 minus 2 squared times 0 minus 1, which gives you negative 2. Negative 2, the 0 minus 2 is negative 2 squared is 4. 0 minus 1, negative 1, and then I multiply negative 2 times 4 is negative 8 times negative 1 is positive 8. So this is the point 0, 8. Now we could discuss symmetry. Again, not required, although I just don't want to leave it out. So you have negative 2 times negative x minus 2 squared times negative x minus 1. Now, to do this, you would have to expand all of this. And if you get the same as the original function, then you have an even function. If you get the opposite signs of the original, you have an odd function. If you have a mix and a match, then you have neither. To me, it's not worth it for this factored function, because not only would you have to expand this, you would have to expand the original function. Matter of fact, it'd be easier to expand the original than plug negative x in there. So I just don't think it's worth it, folks. Symmetry is just not worth it. What we need to do next is plot a bunch of points. So what I'm going to do is I'm going to skip to our graphing page and list our zeros, okay, and I didn't write them as x-intercepts, but as x-intercepts, this is the x-intercept 2, 0, and 1, 0, and then we have a y-intercept 0, 8. So again, to recap, 2, 0, 1, 0, and a y-intercept 0, 8. And so let's plot. So 1, 2, 3, 4, 5. Now, I don't want to do a y-scale until I know what kind of y's I'm going to have. I know I have an 8 and a couple of zeros, but let's do a t-table and complete that before we determine what to put on our y-scale. And if you want, you could always put these values directly on your t-table so you don't forget about them. Now, we need to plot these points first. Let's do this in green. So I've got 2, 0. I've got 1, 0, and the 0, 8 I'm going to wait until I have a y-scale. Now the rule is I'm supposed to plot between and beyond every x-intercept. So on the left, I do have a y-intercept, but let's plug in something else as well. So let's say negative 2. Okay, negative 2, negative 1, either of those would work just fine. We do need to plug in something between 1 and 2. I know you don't want to do that, but 1.5. You got a calculator, so you can do that. And then something on the other side of 2, like 3, 4, 5, let's plug in 3. So I'm going to calculate g of negative 2. It's going to be negative 2 times negative 2 minus 2 squared times negative 2 minus 1. Be real careful with this, because it's easy to make mistakes. This is negative 4 squared times negative 3. So it's negative 2 times 16 times negative 3. And then type that in your calculator if you need to. And I get a result of 96. Okay. Now I'm going to do the same thing with 1.5, but I'm going to rely on my calculator a little more. So g of 1.5 is negative 2 times 1.5 subtract 2 and then square it times 1.5 subtract 1. Okay. And then directly in my calculator, results in negative 0.25, and then I substitute in 3, so I have negative 2 times 3 subtract 2 squared times 3 subtract 1 gives me negative 2 times 1 squared times 2, and that's going to give me negative 4. And when I want to plot these points on my XY axis, but I can't do that until I have a Y scale going on. And notice we got a 96. So maybe we want to scale this every 10. So I could do, say, 10, 20, 30, 40, 50, 60. I think I'm going to extend my axis to 70, 80, 90, 100, and negative 10, negative 20, negative 30, negative 40, negative 50, negative 60, negative 70, negative 80, negative 90, negative 100. So there's 100 and negative 100, and that's a scale of 10. So when I plot my points, I have the point 2, 0, 1, 0, and 0, 8. And remember, this is 10, so 0, 8 is about right there. And then I have negative 2 up here at 96. 1.5 is teeny tiny, negative 0.25. So that, and notice it's negative, so it's just below the x-axis. And then 3, I have negative 4. Okay? Alright, and honestly, it might have been better to plug in negative 1, and I would have got a smaller value, and I wouldn't have to scale this with such big values in between, but we still get a good looking graph. We connect the dots. Okay. Now notice it comes down here, it comes below the axis, it just touches, and then it's going to go back down. Now how do I know that? Okay, well remember our end behavior. Let's go back to the previous page. Our end behavior is the left is up and the right is down. Let's take a look. We do have the left up and the right is down. The next thing that's really important is right here in the middle of the page, at x equals 2 we have an even multiplicity. So I did write it down, but with an even multiplicity, the graph just touches, and the odd multiplicity, the graph crosses the axis. So at 2, notice the graph just touches right here and goes back the other way. It just touches, whereas at 1, the graph crossed over the axis. So notice the difference. Okay, let's try one more graph before we call this quiz. So if we follow our steps, the very first step is to discuss end behavior. So what is the left side of the graph doing? What is the right side of the graph doing? And to discuss end behavior, we need to be aware of the degree and the leading coefficient. What matters about the degree, is it odd or even? Well, it's a degree 4, and that's an even value. On the other hand, the leading coefficient is a positive 1. Remember, the leading coefficient is always the coefficient associated with the term in your degree that gives you the degree. And what matters there is that's positive. If you have an even degree and a positive leading coefficient, that means both sides are pointing upward. The next thing is to calculate zeros. So we have x to the 4th plus 2x to the 3rd plus 9x squared plus 18x. And we factor. Okay, so greatest common factor there is x to the 3rd, and you have x plus 2 factors out. Here you have a plus 9, and that's x, 9x, and that leaves an x plus 2. Notice the important thing is they both have an x plus 2, which can be factored out, and that leaves x to the 3rd plus 9x. Look, there's a greatest common factor right here. As a matter of fact, in the beginning there was a greatest common factor, and we should have pulled that out. But if we don't, that's okay. It'll come out later. So I'm going to pull this common x out. I'm going to write it in the very front, even before the x plus 2. So if x comes out of here, that leaves x squared, and x comes out of here, that leaves plus 9. Now it's time to set each factor separately equal to 0. So I have x equals 0, x plus 2 equals 0, and x squared plus 9 equals 0. So there is one of my zeros. X equals negative 2 is a second 0. Now here I'm going to subtract the 9 over, take the square root of both sides, and that's going to give me plus or minus the square root of negative 9, which is plus or minus 3i. Now these are zeros, but they are not x-intercepts. So I'm next answering the question, are what are my x-intercepts? And my x-intercepts are 0, 0 from here, and negative 2, 0 from here. These guys are not x-intercepts. They are zeros. But as far as the graph goes, this means nothing on the graph. Now, 0, 0, the multiplicity only showed up once, is 1, so that means the graph crosses. Okay, and in negative 2, the multiplicity is 1 also, so the graph crosses there also. Next, I want to find the y-intercept. So that's y equals 0 to the 4th plus 2 times 0 to the 3rd plus 9 times 0 squared plus 18 times 0, which just gives me a big old 0. So 0, 0 is my y-intercept. Now I'm going to move all this info to the next page with our xy axis. And remember, we had intercepts of 0, 0, negative 2, 0, and I had a y-intercept of 0, 0 also. So that's all the information I have. It doesn't look like much information. Let's get a scale going on here. So 1, 2, 3, 4, 5, and then 1, 2, 3, 4, negative 5. Now again, I don't want to do a y scale until I know what my y values are going to look like. So when I plot this, I need to plot 0, 0 and -2, 0. And the rule is I have to go between and beyond every x-intercept. So I need to pick something on the left of this -2, for example, -3. We got burned last time when I picked 2 away because the value was so high, so I'm going to pick right next to it. Then something between these two, maybe -1, and then something to the right, maybe +1, 2, 3, 4. Again, I get burned when I got too far away from my x-intercept, so maybe let's pick something closer to it, and so we don't have to worry about such huge positive or negative y values. All right, so calculator may come in handy here, and again, warning, we may get some big numbers. So I'm going to do h of -3. That's going to be -3 to the 4th plus 2 times -3 to the 3rd plus 9 times -3 squared plus 18 times -3. Now I suggest pausing it for just a minute, just like I'm going to do. Go to your calculator, plug this in, make sure you're doing it correctly, and we'll see if we get the same value. So when I paused it, and you went to my calculator, I got 54. Okay, so we can check it again, -3 to the 4th, 2 times -3 to the 3rd, 9 times -3 squared, and then 18 times -3. All right, so 54. Now let's try -1. Now that one I may be able to do by hand. So -1 to the 4th plus 2 times -1 to the 3rd plus 9 times -1 squared plus 18 times -1. So -1 to the 4th is +1. -1 to the 3rd is -1 times 2. That's going to give me -2. -1 squared is +1 times 9 is 9. And 18 times -1 is -18. It's going to give me 1 minus 2 is -1 plus 9 is 8 minus 18 is -10. And then when I plug in 1, that should work all right as well. 1 to the 4th plus 2 times 1 to the 3rd plus 9 times 1 squared plus 18 times 1. So it gives me 1 plus 2 plus 9 plus 18. So it's going to give me 1 plus 2 is 3. 3 plus 9 is 12, and 12 plus 18 is going to give me 30. Okay, so I want to plot these points, and I want to go back and take a look at my zeros. Check this out. I listed my zeros. We talked about the multiplicity, that it crosses over on both of those, so we need to keep that in mind, as well as we need to remember the left side is going to be pointing upward, and the right side is going to be pointing upward. But our points should point that out to us. So let's go back to all of our information and let's plot these points that we have. Okay, now to save a little bit of space here, let's get rid of our calculations. Okay, I know you've already got all that done, so I'm going to erase our calculations because they're just in the way up here. And I've still got to put a Y scale on. And I thought these numbers might get really big, but you know what? They didn't. And why do you think maybe they didn't, as I'm erasing all this? It really wasn't all that bad. Probably because I didn't plug in big numbers. I even thought the -3, though, would come out a little bit larger. But because it was negative, the signs alternated. But if you start plugging in positive numbers, these are going to get real big fast, as you can imagine. All right, so -3. 54. So again, I'm forgetting, I got to put a scale on here. So if we want to go up to 54, let's say this is 10, 20, 30, 40, and there's 50 right up there, which means we got -10, -20, -30, -40, -50. So let's plot these points. -3, +54 would be right around where my x squared is living. Okay. Probably didn't put that over to the left enough. Let's make that look a little bit better. So -3, 54. How about where the plus is living rather than where the x squared was living? Okay. -1, -10. Remember, this is -10. So that's here. And then +1, 30 is right here. Okay. So I connect the dots left to right. Remember this 0 I'm supposed to cross over, and this 0 I cross over as well, and that goes up forever and up forever. Again, does that match our end behavior? Look, it does. Both sides up. There we go. And I know this looks a whole lot like a parabola, doesn't it? But that's what happens when you get two of your 4 zeros are imaginary. It kind of reverts back to a parabola shape. Also, I want you to keep in mind that these are not perfect graphs. When you take a calculus class, after you take a trigonometry class after this course, you're going to get really good looking graphs because you're going to be able to calculate maximum and minimum values. But right now, we don't have the skills to calculate maximum and minimum values, so what you have is an approximate graph, not the real thing. Hope this helps. Let me know if you have questions.